Hello, good morning. Today I'd like to show you some of my POPOCATEPETL samples. And I'm about to select some samples together with some colleagues for further research. And so I brought them out of the box and now they're here in the rock room, and I'd like to kind of record this and run you through them. I have 4 locations here, and I was focusing when I was doing the field work on Magma-Crust interaction, and POPOCATEPETL, or POPO for short, sits on a carbonate platform, and this is very important because it interacts with its surrounding. And Popo is quite a towering volcano. It sits high above Mexico City, and it is quite dangerous. It can be explosive. It has these irregular, erratic outbursts. Some people call them CO2 or sulfurous burps. So there's a lot of gas coming out quite unexpectedly at times, and my hypothesis is this connects to magma-crust interaction. So let's have a little look here. Here is some samples I picked up from a quarry a little bit further away from the actual Popo volcano. It's called Nealtican, and here we have a lava flow, a nice lava flow. This is the lava here, and you see it's got nice feldspars, a little bit of pyroxene, and typical subduction zone intermediate, mafic to intermediate lava. But what it also contains is these calc silicate inclusions, and indeed they're actually made of typical skarn type minerals. We have green diopside and maybe even some hydrous versions or alteration products of that, and we have the white wollastonite, and this is typical for magma carbonate interaction. And you see a reaction rim, and actually there's some bubbles in there and some dark minerals. There may even be garnet in there. And here just to the side of it we have a few more of those. You will see that here the interaction is quite spectacular, quite irregular. So the lava or the magma was eating into this material, and this was partly metamorphosed during the process, or already maybe in a contact aureole and then incorporated. People sometimes talk about skarn recycling as a secondary process after you make the skarn, but of course you can also do some of these reactions in the conduit while transport, but we'll have to find out how long it actually takes. So here's a bit more of this kind of material. Here we have another greenish skarn type or calc-silicate type rock, and this is an inclusion in the lava, and this is also from the Nealtican lava flow. Here's a different one, and you see the bulbous texture here. Here we have the contact between the lava and the calc-silicate inclusion, and it's got some larger crystals here as well. So this is going to be very exciting to look at in more detail. In addition, we have, of course, some specimens of the clean lava, but there's also some small fragments in there, so we may want to have a look at this and see what they are made of. And here's another specimen of bubbly lava from Nealtican. I remember that picking up some of these lava pieces was a little dangerous, because under one of them there was a big scorpion, and I threw the lava away rather quickly, but nothing happened. So, and in addition to the lava at the Nealtican site, we also picked up some other xenolith. There's some felsic ones that were likely in the lava, but they were actually put away by the miners. So we had a pile of them, and we had picked them up from there. But the spectacular thing is these marbles here. So this is metamorphosed limestone, which hasn't really reacted too strongly. We still have a lot of calcite in there, maybe a little bit of other minerals like wollastonite, which is also white, but this is dominantly calcite. And here you see the nice shiny faces, typical for marble, and this is the first stage of the reaction between the magma and the limestone. So here's another sample of this marble type rock. And over here we have a bit more lava with inclusions. Here's another calc-silicate inclusion, and here is yet another calc-silicate inclusion, and down here we have a few more marbles. So this marble looks a little less clean. It's got a little bit of a darker tinge to it, so there may be some other minerals in there, but well, looking at the shine of the minerals, this is dominantly calcite as well. This calcite here, this marble here is quite nice because the calcite is a little pink, so it looks quite attractive. So, and what we also picked up is these larger crystals. They kind of look like quartz. This is also from Nealtican, but they were strewn on the ground, so I'm not entirely sure. We have to see whether we discover similar ones in the calcsilicates or in the lava in order to make sense out of them. This is why they're lying a little separately. But let's move on. So here we have another site. This is Paso Cortes, Cortes. This is where Cortes was going over the mountains towards Mexico City. And this is at a high altitude. I remember that I was gasping for air. This was above 4,000 meters of altitude. And this was a big pyroclastic unit, which the local people named the Tutti Frutti eruption because it's strewn with fragments. And what we picked up here is also marble again. And here's another one of the marble type rock. And yet more marble, but this one is not as clean as the other ones. And up there we've got a really nice marble actually. So here with the nice calcites. So, and in addition, there's some calcsilicates. So here, have a look here. And this is really rich in wollastonite, the white mineral, and diopside, typical skarn type assemblage. And they can be quite large. They can be football sized at this side. I remember that carrying them up to the car was quite a challenge. Although normally you wouldn't think much of carrying a rock of this size, but at 4,000 meters altitude, everything becomes rather hard work actually. So, and here's another one. Here's another inclusion in lava. So this is a double inclusion. There's a lava inclusion that was in the pyroclastic rock, which itself contains a calcilicate inclusion. You see a reaction boundary here. And this is an interesting rock. So here you see the boundary as well. We also have some hypabyssal rocks, microcrystalline to medium-grained plutonic rocks that are present in the Nealtican pyroclastic unit. And these might be interesting to tell us something about how deep the magma reservoir was located, but that requires a little bit of an extra job in addition to the magma-crust interaction study. So here's a larger one, and it's not very pretty looking, but you can see a boundary in there. And here is some kind of igneous rock, and here is the probably formerly clay-rich material of this particular country rock. And then we have some interaction between these two, and there's yet another boundary visible here on this side. Here's a rather nice specimen, and here we see another calcilicate that's included. There's a little bit of crystallization. I think the magma here used the xenolith as a nucleation surface. There's small crystals forming around these two xenoliths here. The two might even connect in 3D. Well, here it's a larger one on the other side. So it seems that they were fragments and they were in the state of disintegration. And here's a small one that had detached, and you see a reddish reaction horizon surrounding it, and here's a very fine-grained margin. Sometimes these fine-grained margins are actually metal-rich, iron-rich, and not surprisingly, you can have iron skarns, which are sometimes even mined. And this is a magnetic pen, but it doesn't really react. Oh, a little bit, very, very tiny reaction response from the magnetic pen. So there's a little bit of iron oxides that have formed here. And a similar sample here. So we have a reaction zone here, and indeed there is a little bit more of the magnetite, and this I tested earlier. This is actually magnetic. So there we have some magnetite in there, and this formed as a reaction product between the calcilicate xenolith, which is here, and the lava, which is here. So this one seems even zoned with a diopside outer rim here from the margin inwards and a wollastonite interior. If you imagine this was a larger xenolith once upon the time before it got disintegrated, then this would imply that we had a zoned xenolith here. So this reaction may have happened while the xenolith was entrained in the original magma. So, and here, the last site I'd like to introduce you to, it's called Buena Vista, the nice view. And here we have more of the same type. We have calc-silicate rocks. And here I'll show you one, the greenish rock. The greenish color is rather typical, and there's some bubbles in there, so gas was involved. And limestone would, or carbonate-rich materials in the crust, on heating, they would release a lot of CO2 and probably also sulfurous components. And this has climate relevance in addition to potentially influencing the explosiveness of the volcano. And here's just another example of a rather kind of, crumbly rock. And this looks a bit like it got a bit of thermal cracking. And it's rather, well, brittle, and it falls apart already. You hear the bits falling down. And here we have different kind of layers of greenish and darker minerals. So this is going to be an interesting object of study. And here we have a similar type specimen, maybe even related to the first one. But here you see some kind of empty spaces. This is likely where gas was concentrated. And we have some samples here which are similar. This is also calc-silicate xenolith, and you see the open spaces here. So there was gas involved, there was likely pockets of CO2 in this sample when it formed. And if you look at it under the microscope, you see that some of the skarn minerals were growing into these voids. So there was gas there, and the empty spaces were increasingly filled with crystallization, but crystallization did in some cases not manage to fill the entire empty or gas-rich space, and therefore we have these voids or these vesicles in the skarn-type crystal-rich rocks here. So we also have some more of these plutonic fragments here, and here's a nice one. So they might tell us something about where the magma chamber was located if we do barometry on them. So we have some nice kind of mafic faces here, but a lot of feldspar in there as well. This looks of intermediate composition. And here's a large guy. And again, we have these trails of vesicles in there. So some of them, as I said, can be actually soccer ball size and quite spectacular. So a lot of gas must have been released. So this was my quick run through these rather spectacular samples, and I think there's a lot to be learned about what volcanoes do in terms of CO2 emission and what they do in terms of climate influence. Some people say the volcanic contribution is very, very small, maybe 1% of what CO2 emissions are on the planet, in terms of natural as well as anthropogenic contributions. But when we think about the crust playing an extra role, there could be quite an unknown number, an unknown quantity of extra CO2 and actually SO2 as well, because many of these rocks contain also sulfurous material. That could be emitted as well. So there's a big question mark, there's an unknown there. Magma itself might not bring so much CO2, but if we cook up the crust, if we heat it up and metamorphose it, a lot of the CO2 will be released. Don't forget, limestone has 42% of CO2 stoichiometrically, and most of these calc-silicates have very, very little CO2 left. So a lot of degassing must have happened in order to produce them. And we're trying now to find out how much this could have been and what it could actually be doing in a broader context. So this is my little kind of run through. I hope you found this interesting. Thank you for your attention, and I hope to see you soon again. Bye bye.